It is divisible by only by itself and 1. Again, the stringent rule gives you a hint that whether a prime range you have given is finite or infinite. Calculate the set of primes or check for the primality of a number. None of these primes were in the original list. We didn't have those primes in the original list. Hello students, welcome to the next session of Network Security. I am Dr. Soumeshri from Department of Computer Science, Vidhyaashram First Grade College. Let's start this session with some of the basic mathematical concepts that are used in the cryptography. Okay, so the first thing we need to know is about the primes. You know about the primes, isn't it? You have already studied so many times in the elementary level, school level. What is a prime, isn't it? Because if somebody asks you, what is a prime? What answer you will give? It gives the definition that a prime is divisible only by itself and 1. A number can be called as a prime number if it is divisible by 1 and itself. That means it is a prime which is divisible only by itself and 1. None other numbers will be able to divide that number. Such kind of numbers are called as the prime, isn't it? So we have the specification of the prime. Prime needs to have only 2 divisors, that is itself and 1, not less than that, not more than that. The stringent rule of prime is it is divisible by only by itself and 1. Again, the stringent rule is it must have only 2 divisors, not less than that, not more than that. Okay, so we have 3 types of numbers in positive integers. One is the normal number, which is having exactly 1 divisor, 1 number. Then we have primes, which is having exactly 2 divisors. And last category is the composites, which has more than 2 divisors. So we have 3 types of values that can be used in the asymmetric key cryptography, which most of the times uses the set of primes in its crypto system. Okay, so we have 3 types. In this, the prime is the main thing which can be used. Along with this, we use a term known as co-prime. What is a co-prime? If you take 2 numbers A and B, they are said to be co-prime if the GCD of A and B is equal to 1. If 2 numbers and their GCD is equal to 1, then those 2 numbers are called as the co-primes of each other. Like 1 will be the co-prime of any numbers up to n. Okay, so whenever you take say 1, 100 or 1, 20, the greatest common divisor or 2 primes, 1, 7. So GCD will be 1. So if the GCD of 2 prime numbers is 1, then they are called as the co-primes or relatively prime. Okay, so the co-primes are used to calculate or will be used in the encryption as well as the decryption process. Let's check these prime sets. When you look at what is the smallest prime we can use, the smallest prime is 2, not 1. The smallest prime is 2, which is divisible by 2 and 1. You may ask that 1 is also a prime. Why 1 is not considered as a prime is 1 has only 1 divisor. It is divisible by itself, no other values. But the stringent rule of prime is that it needs to have two divisors, one itself and another one. One and itself must be the divisors. So 1 has only divisor. That means 1 is not a prime. Therefore, the smallest prime in the set of integer numbers is the 2, which is divisible by 2 and 1. Whenever you get a program in any programming language to check the prime or list the set of or print the set of primes, you must start your prime number by 2, not by 1. Okay, so 2 is the smallest prime in set of prime values. Okay, now let's check another example. List the primes smaller than 10. What are the values that are smaller than 10? There are 4 primes that are less than 10. That is 2, 3, 5 and 7. Okay. We need to note an interesting thing, that the percentage of primes in the range from 1 to 10 is 40%. Out of 10, 4 numbers are primes. The percentage decreases as the range increases. If you take 20, how many you get? 2, 3, 5, 7, 11, 13 and 17, isn't it? So we get 7 prime numbers. They are 2, 3, 5, 7, 11, 13, 17, 19. You get 8 prime numbers, isn't it? So these are the set of prime numbers. That means the percentage will increase as the range of prime value or range of number increases. The number of prime numbers will usually decrease. Okay, this is the thing we need to remember. Okay, now we shall check about the cardinality of primes. What is cardinality of primes? So what is cardinality of primes? The cardinality of primes gives you a hint that whether a prime range you have given is finite or infinite. Okay. Now we have infinite number of primes. That means we have the infinite number of primes in the integer values. Okay. So we have, how do you get the number of primes in a value? How do you calculate the number of primes in a value is using this expression, that is n divided by logarithmic n less than phi of n, that is sum of n we take, less than n divided by logarithmic n minus 1.08366. So this is the expression which will help you to calculate the number of primes in n number of values. Okay, suppose if you take 1250 as the number, what are the primes that are available from 2 to 1250 will be calculated by this expression. Okay, now let's take an example. As an example, we check, assume that the only primes are in the set are 2, 3, 5, 7, 11, 13 and 17. So here P value is 510510. P is the final primality value. Okay, and P plus 1 is 510511. Okay, however 510511 is equal to 19 into 97 into 277. It is already calculated with set of primes. None of these primes were in the original list. We didn't have those primes in the original list. Therefore, there are 3 primes that are greater than 17. So you'll get by multiplying these values, you will get this value. That means you have 3 primes that are greater than 17. Along with this, we have 3 more primes. Okay. Next is find the number of primes less than 110 lakhs. Right. So how do you calculate the number of primes? The approximation gives the range 72,383 to 78,543. So the total number of primes or actual number of primes we get from 2 to 10 lakh is 78,498 based on the percentage of the occurrence, and the expression that we have listed here will be used to calculate the actual number of primes that can occur within a range. What is the use of these primes calculation is to get the set of values that can be used in converting the plain text to the ciphertext or during the encryption process. Okay. Next, we shall move on to the next concept, that is checking the primeness of a number. So how do you check the primeness of a number? Well, if you given a number, say 10,258 or 57, how do you calculate that this number is a prime or not? How do you calculate that? We have a method for this. Given a number n, how can we determine if n is a prime or not? You may have tried the program of checking a prime in set of n numbers, isn't it? Any C or C++, Java, whatever it is. You may have checked whether the number is a prime or not. How do you calculate that? The answer is that we need to see if the number is divisible by all primes less than square root of n. Okay, you have to check for the number which you obtain by the square root of n. Numbers less than square root of n. And we take those numbers and check they are going to divide the square root of n number. So then we know that this method is not inefficient, but it is a good start. This method is inefficient. It is not much efficient in finding out whether a number is prime or not. But it is the best method that we can use, or the good start to check a number prime or not with the minimum range of numbers. Okay. Example, if you take 100 or if you take 97, how do you find out whether the 97 is divisible by others or 97 is prime or not? Is you have to take the square root of 97. So square root of 97 is not possible, but the nearer one we get is 10 will be 100. That means the nearest prime number which is nearer to square root of n or square root of n calculates 9. If you take the integer value, it checks 9. What are the numbers less than 9? Prime numbers 2, 3, 5 and 7. So if you check whether the 97 is divisible by these values 2, 3, 5, 7, you will get to know if it is divisible, it is not a prime. If it is not divisible, then it is a prime. You can check with that. 97 is neither divisible by 2, nor divisible by 3, nor 5, nor 7. In such a case, you can say that 97 is a prime. This is the same logic we use in the program, isn't it? So find out the square root and check for the values less than that, isn't it? So if you take another example, say 95, we get the square root of 95 is again 9 only. If you check for the divisibility by the prime numbers less than 9, 2, 3, 5, 7, 95 is not divisible by 2, 95 is neither divisible by 3, but 97 is divisible by 5, isn't it? 5, which is divisible, 95 is divisible by 5 and not divisible by 7. That means if it is divisible by 5, this is not a prime number. So you can check the primality of primeness of a number by taking the square root of the number and checking for the divisibility of that number by checking the primes less than the square root of that number. Okay, so this is the test which we can do for checking the primeness of a number. Like next, we shall go to the primality testing. What is this primality testing is all about? It is finding an algorithm to correctly and efficiently test a very large integer. We need to set the key. So what we'll do is finding an algorithm to correctly and efficiently test a very large number and output a prime or a composite. You have to output a prime or composite. It has always been a challenge in any number theory. So the algorithms that deal with this issue of calculating the prime numbers in very large integer and output of a prime, okay, is divided into two broad categories. We are going to divide that into two broad categories. One is the deterministic algorithm, another is the probabilistic algorithms. We use two algorithms to find out the prime of a large integer and prime of a composite value or output of a composite value will be calculated by the deterministic algorithm and the probabilistic algorithm. Let's check these things. We have the deterministic algorithm. How does the deterministic algorithm will execute? We have the divisibility algorithm which helps in getting the or checking the divisibility of a number. We take the divisibility test for determining with the deterministic algorithm. Okay, n is the number which is test for primality. Okay, now we have r assigned with 2, the first prime. Then while r less than square root of n, that is checking for the primeness. If r divisible by n, that is square root of n, then return composite. Otherwise, r equals r plus 1. So it is incremented to next prime value. Then in final, return a value prime. This is a deterministic algorithm which determines the value whether it is prime or not. Example, if you take, assume that n has 200 bits. Okay, what is the number of bit operations needed to run the divisibility test algorithm to test whether a number is divisible by prime numbers or not? If it is divisible, it is not a prime. If it is not divisible, then it is a prime. So you have to check or you have to use the algorithm to check the divisibility on a number. Okay, the solution what you can give is that bit operation complexity of this algorithm is 2 to the power of nb by 2. So we have n number of and base by 2. We are taking half of 2 to the power of n. This means that the algorithm needs 2100 bit operations. On 200 bits, you need to perform 2100 bit operations. On a computer capable of doing 230 bit operations per second, if it is capable of doing 230 bit operation per second, the algorithm will need 270 seconds to do the testing. Okay, that means it is the time that will be used by the computer to check the primality of a number or primeness of a number by using the deterministic algorithm. In this, we have an improvised AKS algorithm. AKS algorithm uses this expression O log of base 2 n to the base b. N will be to the base b power to the power of 12. We are using this expression to calculate the set of primes or check for the primality of a number. Okay, here O is the time complexity of a number. O is the time complexity of a number. So, example you can take is, again, assume the 200 bits example only. What is the number of bit operations needed to run the AKS algorithm? Okay, the solution you can give is, this algorithm needs only log 200 to the base 2 to the power of 12 will give you these bits number. These many bit operations are given by this algorithm. On a computer capable of doing 1 billion bit operations per second, it is going to do 1 billion bit operations per second. The algorithm will need only 40 seconds. Okay, so when compared to the deterministic algorithm that we have already used, it will take 270 seconds with a computer capable of handling 230 bits per second. We have a computer capable of doing 1 billion instruction set per second. It can execute 1 billion instructions per second. It can calculate the primeness of a number within 40 seconds. Okay, so AKS algorithm is much more better than the deterministic algorithm that we have already studied. Okay, let's check with the probabilistic algorithm. The only test or the test that we can go with the probabilistic algorithm we use is the format test or the format primality test, you can call it as. So, this is the basic test which tells that if n is a prime, if the number n is a prime, that means a to the power of n minus 1 is congruent to 1 mod n. So, this is the expression that is given by the format primality test, which says that if n is a composite, it is possible that a to the power of n minus 1 is congruently equal to 1 mod n. That means there is no clarity that how to calculate the prime. Even if it is a prime, a to the power of n minus 1 may be equal to 1 mod n. Even if it is a composite, it is possible that it may get the same result. A to the power of n minus 1 is congruently equal to 1 mod n. But the thing is, probability will be less for the numbers who are composite and probability will be more for the n which is a prime. So, how do you differentiate between prime and composite in probabilistic algorithm is based on the probability rate of a number. If n is a composite, same thing holds good, but the thing is probability will be less in case of the composite number and it will be more in case of prime numbers. Based on the probability of the numbers, with this expression we can calculate or we can analyze whether the number given is a prime or not. So, this is one of the probabilistic algorithm, that is the format test. Then we have the square root test that you can take again in a probabilistic algorithm. What it says is, if n is a prime, square root of 1, if you take square root of 1 mod n, it will be equal to plus or minus 1. What it says, if n is a prime, the square root of 1 is either plus 1 or minus 1. Suppose if n is composite, if it is not prime, if it is composite, the square root is either plus or minus 1, but there may be other roots. Along with plus or minus 1, you may also get other roots which makes or which indicates that the number is not a prime, rather it is a composite number. Okay, so based on the square root of a value or square root of a n and taking the mod n with one value square root of 1, you can check whether the number n is prime or not. This method of using the square root of 1 is called as the square root primality test. Using the square root value of 1, making with the modulus operation with n, if you get plus or minus 1, then it may be prime. If it is a composite, you may get plus or minus 1 for the same expression, and possibly other values will also be included with the composite numbers. Using that set of values you get with this expression, you can conclude that whether the number is prime or not. Okay. Example we shall take, what are the square roots of 1 mod n if n is 7? If it is a prime, what is the square root of 1 mod n? The only square roots are 1 and minus 1, plus 1 and minus 1. We can see that 1 to the power of 2 we take, that is 1 mod 7, and minus 1 to the power of square is equal to 1 mod 7. Okay. Same thing will be carried out. 2 to the power of 2, 4 mod 7, will get 4 only. Again, minus 2 is 4 equals 4 mod 7, plus or minus will be taken. Note that we don't have to test 4, 5, 6 because 4 equals minus 3 mod 7. Minus 3 square is 6, 9 we get. 9 mod 7 is 4 we get. That is 3 to the power of 2. Minus 3 to the power of 2 is 9. 2 mod 7 we get. 5 equals minus 2 mod 7 and 6 equals minus 1 mod 7. So you can check for the primality using the square root value of the 1. Next we have another Miller-Rabbin test. What is this Miller-Rabbin test is going to do? How it is going to calculate the primality is, it is the idea behind the Fermat primality test. This is the basic test from which Fermat test was improvised version of Miller-Rabbin test will be called as the Fermat primality test. It uses the expression a to the power of n minus 1 equals a to the power of n into 2 to the power of k. Like this expression will be used, and k times the square root will be calculated to get the primality. Okay. The Miller-Rabbin test needs from step 0 to step k minus 1. It is calculating or it is checking for the primeness of a number by using the base as a and making the square root for the successive numbers of the m. Okay, this is the Miller-Rabbin test. We have an algorithm which are pseudocode for Miller-Rabbin test. How it is going to calculate? It calculates n, comma a, where find m and k. You have to use set of values m and k such that n minus 1, that is number n, say if it is 50, 50 minus 1 is equal to m into 2 to the power of k. Okay. So n is the number and a is the base we use. And we calculate the a to the power of m mod n which gives you the value of t, that is the Fermat test. If t is equal to plus or minus 1, if the square root is plus or minus 1, then return a prime. So the Miller-Rabbin test includes the square root test as well as the Fermat test. Okay, if the t value is equal to plus or minus 1, then return a value prime. For I1 to k minus 1, that is set of values you have to take, t square mod n value will be assigned to t. Again, if you calculate the t, if it is equal to plus 1, it is a composite. If t is minus 1, you have to return it as a prime. Okay? Or else, if nothing works in this, then it is a composite number. This is how we can calculate the primeness of or primality testing of a number by using the Miller-Rabbin test, either the square root test or the Fermat test. So the strongest one and the better approach for checking a number prime or not is the Miller-Rabbin test, which includes the concept of Fermat test as well as the square root test. Much more about the mathematics of cryptography will be calculated in the or explained in the next sessions. Thank you.